I got like 2 words.
Okay, we were, remember yesterday, we kind of got interrupted here in the middle of our cool geometric proof. We were going to take a look at, the whole point of this, recall, was we wanted to find out what the value of this indeterminate form of the limit was. We want to know what the limit of sine theta over theta is as theta approaches 0. Now, it appears to be 0 over 0. It's indeterminate, but we got to pin it down to an answer. Okay, here's how we were going to approach this. We have these 3 different shapes that I've got kind of, this built this morning, this is kind of cool, you'll like this. We've got this small shape, which is the green one, which goes, well, I can just move it. It's this guy right here. Come on. It's that guy right there, right? Okay, so he's that inside triangle. And it's a right triangle. In fact, let's move it out here to mess with it. If it's inside of a unit circle, we said, then what did we say the area of this guy was?
Sine theta over 2.
Sine theta over 2, good, because we knew that the base of this thing had, from here to here was 1, right? And we said that this is theta in here, right? And so, if that's theta and this is 1 and this is a right triangle, then what's the height of that thing? Sine theta, right? Because we know in a right triangle, we know that if this is our theta, then by SOHCAHTOA, sine is defined as the ratio of, well, hang on, this whole thing right here is of the, yeah, we want the hypotenuse to be 1, right? And the height of this guy, this is also 1, isn't it?
Yeah.
Right? And so if we're just focusing on the little right triangle, then we know that this is the opposite side and that's the hypotenuse, right? And we know by SOHCAHTOA that sine theta equals opposite over hypotenuse. And so if that's 1, then this must be sine theta, right? Does that make sense? Okay. The ratio of this mystery side, if we called it x, x over 1 must equal sine theta, because that's opposite over hypotenuse. And so x therefore equals sine theta algebraically. Okay? All right, so let's put, so we know the area of that guy now. I'm going to group all that stuff and we'll slide him back. So he goes over there. And let's grab this guy. We'll grab this red sector. I think that's where we left off. Wasn't that where we left off? You guys were going to tell me, you don't know this formula, but you don't memorizing formulas is a terrible idea because you'll just forget them. If we come up with a way that we can simply derive the formula of the area of a sector, then you always remember it. And the way we thought about this, we started thinking about this, was it's a piece of pizza. If this is a piece of pizza who's described by angle theta, what's the angle associated with the whole pizza? You told me yesterday. It was 2 pi, right? 2 pi radians in a complete circle, right? And so, if you want to tell me what fraction of the whole pizza are we eating, what would it be? Say it again. Good, theta over 2 pi, right? It's theta 2 piths of the whole pizza, right? So if we want to find the area of this slice, then how could we use that knowledge maybe to come up with the area of the slice of pizza, given, of course, that we know the area of the circle, right? What do you think? If we're eating theta of 2 pi from the whole pizza, what would the area be? What do you think?
Theta over 2 pi times pi r squared.
Ah, there you go. How about that? Right, we know the entire area is pi r squared, and if this represents theta over 2 pi of the whole area, then I could just multiply the area by theta over 2 pi, right? Now, what's the radius of our circle again? 1. So the pi r squared really becomes what? Pi, yeah, pi times 1 squared is just pi, right? So the area is pi. And so, what's the area of our sector then? Pi's cancel, right? And so it's just theta over 2. How about that? Okay, make sense? There's the area of our sector. So let's keep track of these areas while we're at it here. Let's make a list. So the green area we said was sine theta over 2, right? The red area we're now saying is theta over 2, okay? And then let's finally take care of this guy back here. Let's look at this blue area. Okay, we said that's 1, right? It's a right angle. And now what? This is theta, right? How am I going to find in order to find the area, it's half the base times the height, right? So it's 1/2 times 1 times h. Got to find h though.
So it would be tan theta.
Yeah. How'd you get that? Good.
Well, opposite adjacent.
Good. Okay, we know that the SOHCAHTOA relationship that links the side of known length and the side that we're trying to find, the unknown, that's going to be opposite and adjacent, right? You know, tangent of theta by definition equals h over 1 then. And so h equals tangent theta. Okay, good. So then the height of this is just 1/2 times 1 times tangent theta, or tangent theta over 2, right? Okay, so now we're going to do some tricky stuff with that. And we can agree here, just visually, right, that okay, and we can agree that of those 3 shapes, clearly the green is the smaller area, smallest, right? The red is the medium area, and the blue is the large area, and that's independent of angle, correct? As I tweak the angle here, you know, all those are going to always retain that order of smallest to medium to biggest, right? Everybody agrees? Okay, so then let's look at these. We can order these. Oops. We can order these areas like this. We could say sine theta over 2 is the least. There's theta over 2, the middle. And here's tangent theta over 2. Okay, now let's do some algebra with this. I'm going to multiply all 3 expressions here in this triple inequality. I'm going to multiply them all by the reciprocal of this first expression. So I'm going to multiply them all by 2 over sine theta. And assuming here that this really only makes sense for us if we're considering angles that are approaching 0 anyway, right? So there's really no reason for us to consider weird angles of theta where sine theta is negative or something, right? I mean, we're just going to be we're just looking at values that are approaching 0. Make sense? Okay, so if I do that, then what does that do to my inequalities if I multiply all these by 2 over sine theta? What does this one become? 1, okay? What does this one become?
Sine theta over sine.
Theta over sine theta, right? If I multiply by 2 over sine theta. Okay, now this last one, it's a little tricky. What's tangent? Let me write it as a ratio. Say it again. Sine over cosine. Sine theta over cosine theta, right? So if I think of the tangent theta as being a sine theta over cosine theta, and I multiply by 2 over sine theta, what am I going to get? Let's write that one out. Sine theta over 2 cosine theta. That's tangent theta over 2, right? Times 2 over sine theta. So what do I get? Okay, good. 1 over cosine theta. Okay. Okay. And now what's going to happen? Another question for you. What happens if I take the reciprocal of all those? If I invert all of those fractions, what's going to happen to the inequality signs? They're going to flip, aren't they? Now, why is that? Well, let's take an example with just some static fractions. What if I had something like, we know that 1/4 is less than 1/3, and that's less than 1/2. If I flip all of those, look what happens. This becomes a 4, that becomes a 3, and that becomes a 2. Well, obviously I have to change the signs, don't I? Makes sense if you think about it, because we know fractions get smaller as the denominators get bigger, but fractions get bigger as the numerators get bigger, right? And so when I flip these things around, okay, so if I flip those, this just stays a 1. What's that become? Well, I mean, sine theta over theta. This becomes cosine theta. Whoops. And we've changed the inequality signs around. Okay. But now let's take a limit. Let's take a limit of all 3 of these things as theta approaches 0. Okay. Okay, if I do that, in the limit, what are we going to get here? Let's look at the outer ones first. This guy over here, the limit of 1 as theta approaches 0 is what? 1, yeah. There's not even a theta in there, right? 1 is, the function here, 1 is independent of theta. It's not changing regardless. So I get an answer of 1, okay? Let's look at the blue limit. The limit of cosine theta as theta approaches 0 is what? What do we always try to do if we're taking a limit first? We want to try direct evaluation. Well, what is the cosine of 0? No? 1. Yeah. Okay. Well, now, remember that little theorem I showed you yesterday, the squeeze theorem, right? The squeeze theorem is, we essentially just drew a picture. Squeeze theorem just tells us this, right? If we've got, I'll remind you, whoops. All the squeeze theorem said was if there is, we had some green function that I think we called g of x, I don't remember what we called them. We had some blue function that we called h of x, and we had some red function that was pinched in between the 2 functions, at least in the vicinity of some value that we're interested in, call it c. So in the neighborhood of c, we said that g of x is greater than or equal to f of x, and h of x is less than or equal to f of x, right? Well then, what did we say had to happen if the limits of the ceiling function and the floor function both converged on a single value. What does that necessarily say about the in-between function? It has to get pinched to that same value, right? Because if it's contained between the green on top and the blue on the bottom, and the green and the blue converge on a single value, then it gets squeezed in there with them, right? So we call it the squeeze theorem or the pinch theorem, okay? So then you tell me what's going on with our indeterminate form. What must the limit of sine theta over theta be as theta approaches 0? It's got to be 1, doesn't it? Got to be 1. Isn't that a cool proof? I just think that's a super cool proof because it's all geometric. And the other thing that I think is so cool about this is that it once again shows us how unbelievably useful the unit circle is. The unit circle, if you work at it just a little bit, everything in trig essentially can be represented by the unit circle. It's extremely handy. I mean, it looks like how useful could it be? It's just a circle, but it really is extremely useful. Okay, so now we've got this new fancy new limit. What do we do with it? So let's write this down. So we know the limit of sine theta over theta as theta approaches 0 is 1. Okay, indeterminate. Now we've solved it. We could also, real quick before I jump into something new, if we look at this graphically, we can also see this trend. If I didn't want to do that really cool proof, I could have just sort of finessed it and just showed you a graph, and you all would have told me graphically what the limit was. But I wanted to show you that proof. Okay, if we graph let's make sure we're in radians mode here. Yep. If I graph the function sine theta over theta, or sine x over x, do you guys know how to get to the fraction template on your fancy calculators? This is pretty handy. I mean, you don't ever really have to get there, but it's kind of nice to know how to get there. There's two ways. If you go to the math menu and you scoot over to the math screen, you scoot over to the number menu and you advance up to the bottom of the list because it wraps around. There it is. Okay, it's the numerator over denominator gives you that fraction template. Or there's an even better shortcut. Does anybody know it? Yes, there you go. Good. Alpha, is it 4 or 1? Alpha F1. There it is. Okay. Notice there are, if you hit alpha, you get these 4 different shortcut menus. You get the function menu on F2, which is kind of nice. You get the Y variable is really handy on F4. So you can get right to Y variables if you need to insert those in statistical stuff. And we'll do some of that too. I'm sure you already have. So I can pull up that little fraction template. Oops, but I don't want it there. I want it there. I wonder if you can put it there. I think so. Yeah. Okay. So we'll go sine x over x. And let's go, if I go zoom trig, what do you suppose that's going to do? Let's go back and look at the window real quick. What did that do? I mean, not exactly, but what's that sort of trying to do there? Yeah, it's just a slight bit more than 2 pi. Okay. So it's given us a full cycle before and a full cycle after of a standard sine or cosine function. And then I'm also going to go zoom fit, so it'll fit the screen a little better. Well, this time the height is 1. You can see that this function is clearly approaching a value of 1 up there, isn't it? Right? If I take little bitsy steps, if I trace along, you can see the y value. If I go backwards, it's going down a little bit. As I move to the right, the ant's climbing up the hill towards y equals 1. Right? But when he gets to what would be the top, there's a hole, right? Has to be. The function's not defined there because sine x over x, if I, that's taboo. Can't do that. I can't let x equal 0 because I'd have a 0 on the bottom. I can't do that. So we get a little hole in the function there, but now we know what the limit is, and we can see it there graphically on the screen. All right, so what are we going to do with this? Let's look at a couple problems where this comes in handy. Okay, how about this? What if we want to find the limit of tangent squared x over x as x approaches 0? What do we always try to do first? Evaluate directly. Okay, what's the tangent of 0? Think of it in terms of sine and cosine. Tangent's sine over cosine, right? So sine of 0 is 0. Cosine of 0 is 1. Okay, so what would it be? 0 divided by 1 is 0, right? So I get 0 over 0. It's indeterminate. So what we've got to do then, when I'm faced with a trig limit like this that's indeterminate, I've got to do some trig magic on this and somehow rearrange this algebraically so that I can coax out this known limit. What do you suppose I want to do if I've got a limit then that's written in terms of like tangents, some composite trig function? Yeah, a good strategy, and we're going to use this a lot in calculus throughout the year, would be to write it in terms of the simple trig functions, right? The basic trig functions, sine and cosine. So what's that going to look like then? Okay, sine squared x over x cosine squared x. Good. And now what? My goal is to somehow regroup this thing. And keeping in mind that multiplication is commutative and associative, right? I can break up, like a sine squared is really just the sine x times the sine x. So I've got 2 factors on the top and 3 on the bottom. X, cosine x, and cosine x on the bottom. I want to regroup those in a way so I can get one of these to pop out. Well, we're using x's instead of thetas, but same thing. Yeah, okay. I'm hearing it. So let's dice this up. So we've got the limit of sine x times sine x over x times cosine x times cosine x. And look, if we split this up, so these guys are grouped together, right? Then we got it. Okay. So it looks like limit of sine x over x as x approaches 0 times the rest of the stuff. Sine x over cosine squared x. Okay, now here's where, technically speaking, we talked about this a while ago, but it was a little out of context. It was a little before we got into doing these problems, and so let's talk about it again real quickly. Our properties of limits say that if we have a limit of a product like this, I've got the limit of this guy times this guy. That's the very same thing as saying the limit of the first times the limit of the second. Okay, in the language of the book, I think we said something like this. If the limit of f of x as x approaches a is L, I don't know what they called it, and the limit of g of x as x approaches a is k, right? Then the limit of f of x times g of x as x approaches a is what? Yeah, it's just L times K, isn't it? We can split this up, in other words. We can break this up into two separate limits. The limit of f of x as x approaches a times the limit of g of x as x approaches a, which just gives us L times K. So we know that's always true, right? And so do we necessarily want to take the time to write that out? No, probably not. Probably not. I mean, we know that it is true, but we could just jump, in other words, we could just jump right from here to an answer. We know that we're going to, because we've got a limit of a product, I can evaluate those two limits separately. I don't have to go through the rigmarole of writing it all out as two separate limits because it doesn't really accomplish anything. That's universally true. Does that make sense what I'm getting at? We want to be efficient in the way we show our work in calculus, and so we can just do this. We can just say, this one right here, that limit we know goes to what? That's our special limit. Right? Right? So what is the value of that limit as x approaches 0? By definition, it's just 1, because that's our special trig limit. This other one, look at orange, this guy we're going to have to evaluate directly, right? Now there's a chance it's still going to be indeterminate also, and we've got to do some more work. But is it? No, it's not. As x approaches 0, what's the numerator become? What's the denominator become? 1. So that one is 0. 1 times 0 is 0. We got it. So it's not indeterminate anymore. We know the answer. It's 0. See how that works? Okay. Now there's another one that they give you in the book. They also give you, I can't remember what it is because I always just derive it every time I need it. But I think it's 1 minus cosine theta over theta equals 1. But I better just make sure. Yeah, that's it. Okay, they also give us this guy. And you're welcome to memorize this, but I'm going to show you how you don't really have to. The limit of 1 minus cosine x over x as x approaches 0 equals 1. If I ever find myself in that position where I've got to evaluate that indeterminate form, I always just quickly turn it into one that I know how to do. Oops, that one's 0, sorry. I knew that was, that didn't look right. One of them, the first one we got, sine theta over theta is 0, this one is 1. Yeah. How could we quickly, anybody know how we could do this real quickly? How we could, if we forget that one, how we could turn it into the first one that we just did, the sine x over x? Give you a hint, we're going to multiply this by 1 in some form. Give you another hint. Remind you about the Pythagorean. What's this always equal to? Sine squared x plus cosine squared x. 1. Okay. So now, does that give you any ideas? Could I multiply top and bottom by something in such a way that I could turn the top into a trig function squared? This is right up Juan's alley. He had something like this the other day that was...
Special one.
Okay, what about this? What about this? What if anybody have any idea? I don't want to push this.
Well, is it the conjugate?
The conjugate, yeah.
Okay.
Must have been, right? Because I said Juan is right in his wheelhouse here. So if I multiply by 1 plus cosine x over 1 plus cosine x, look what happens. What's that give me on the top? Okay, yeah, it's going to be 1 minus cosine squared, and in terms of our of our Pythagorean trig identity, what's 1 minus cosine squared? Ah, there's our sine squared, right? We like to see 1 minus sine squared or 1 minus cosine squared. We can make a trade. Okay, and we'll trade all that stuff for a sine squared. And now we just reorganize it a little bit, right?
Yeah.
What do we do?
Pull up the sign.
Pull out a sine. Good. So we've got limit of sine x over x. So we're going to group one of those sine x's in the numerator with the x in the denominator. And then the other one is just going to be a sine x over 1 plus cosine x. Now we can take our limit, right? In the limit that x approaches 0, what does that one become? 1. What does this one become? 0. So I know it's 0. So, and honestly, you can even sort of do that in your head. If you just think, once you've done it once or twice, you can just look at that and say, okay, if I did this, that's 0, right? And so I never remember it. I just always look at it that way. But you're welcome to, if you want to. If you want to commit those brain cells to memorizing something, there you go. Okay. Okay, let's take a look maybe at one more of these, being as aren't we pretty close to being done? We gotta be. God, this is killing me not having this clock. Jeez. Oh yeah. Yeah. How many times do you have to remind me about that? A lot. Yeah. Okay. Okay, I'm gonna skip up. I want to do another one in between, but I want to do this one. I think we're gonna run out of time. So let's try this. What if I had? What about that guy? Now remember, if I want to use our fancy new special trig limit, I got to make it look exactly like that. Ah, okay, good. Okay, did you ever see what we did there? We took out a 1/3. We just factored a 1/3 out of the bottom. So I'm going to rewrite this as the limit of 1/3 times sine x over x as x approaches 0. And you might also remember, you might not too, that we looked at a general case like this. What is the, generally speaking, if I have the limit of a constant times f of x as x approaches a, and let's say we've defined the limit of f of x as x approaches a as being L. Yeah, it's just CL. Okay, and this is an important one. What this tells us is if I have the limit of a scalar multiple like that, if I've got a constant times a limit, I can always pull the constant out of the limit. And those are words, let's say that again, because I'll say that a billion times this year. We're going to pull the constant out front of the limit. Okay? That's handy to do. We're going to do stuff like that in calculus all year, and it's a great technique. It doesn't seem like much right now, but you'll learn to love it later. So we'll take that 1/3 and literally take it out front, and we just end up with 1/3 times our known limit. It's 1/3. Right? Select. Okay, now there's one just like that I want to get to, and if I get through this, we're good for the day. How about if we try something that looks very similar? Let's take the limit of sine of 5x over x as x approaches 0. Okay, now this is a little tougher because that 5 has been swallowed up by the sine function. So I don't have the luxury of just pulling that one out front because it's actually inside of an interior function. Does that make sense? Okay, so it's off limits to us. And yet I do have to make the argument of the sine function match the denominator, right, in order for us to fit that pattern. Let me write the pattern down again. Limit sine theta over theta. As theta approaches 0 equals 1. So whatever I'm calling theta, I have to have the same thing on the bottom. So suggestions? 5 over 5. Why not? What if I just multiply top and bottom of this thing by 5, and I'll just group that stuff, right?
Yeah.
Looks good. What can I do with this 5?
Yeah.
Pull it out front. Very good. Okay, so we're almost there, but there's one more small detail, and we got to deal with even the small details in math. What's the problem? There's one other thing that's not matching up here. Look, I'm trying to get these all to be thetas. Well, let's see. That's a theta. That's good. That matches up. That's a theta. That matches up. But what about this guy right there?
Oh, shoot.
See the problem?
No.
I've got the limit of the sine of 5x over 5x as x approaches 0.
Shoot.
Can we just put a 5 there? Well, maybe we can. Now let's think through this. If x is approaching 0, then what is 5x approaching? 0, right? Because in the limit, now think of it this way. Think of it this way. If I'm going to start from here, and I'm going to cut my distance to the door in half every step, like we did before. I better start a little closer. I'm just going to go like that, and then like that, like that. Well, what if I started 5 times as far away, but did the same drill? I'm going to cut my distance to the door in half every time. It's the same game, isn't it? Different size steps, but wouldn't you agree that the very same result is going to apply? Okay, because ultimately 5 times 0 is just 0, right? So does that make sense then that we can reason that if x is approaching 0, then any constant number times x will also approach 0. It could be a billion times x. Doesn't matter. Doesn't matter how big the number is times x. If it's a static number and x approaches 0, the product also has to go to 0, right? So that's an easy one. We can just, in physics and math, we just say that's a little hand wave. We'll just wave our hands and call it good. And it works. It works. We can just attach the 5 there without having to really do anything special.
So that was 5.
All right. Good day.